Okay guys, we have found the values of p11 of 0 and p11 of 1, right? So this I'm just continuing with the previous lecture number 2. So we had, I guess, we were up to p11 of 0 and p11 of 1. So actually I had recorded this entire lecture while writing this down, but somehow after this part, that is when I started writing from here, the audio in the video was lost. So I've already written down the notes, so I'm going to explain you how this is done. Now p1 of 2, as in case of p11 of 1, this will be equivalent to g1 of n minus g1 of n plus n by 4 wn by 2 n. Now we will substitute the values. N will be from 0 to 1, so if n is equal to 0, then p1 of 2, I will substitute n is equal to 0 here, so it will be g1 of 0 minus g1 of 0 plus n by 4, that is 8 by 4, that is 2, so it will be 0 plus 2 w4 0, that is g1 of 0 minus g1 of 2 w4 0. So if you notice, the guys, in case of even sequence, that is p1 1 of n, there was no multiplication by the dual factor. But in case of the odd sequence, which is p12 of n, that is p12 of 0 and p12 of 1, there will be a multiplication by a dual factor. Also, in case of the even sequence, we had a plus sign here, but in case of the odd sequence, we will always be having a minus sign, right? So similarly, we will be getting values for p12 of 1, it will be g11 of 1 minus g1 of 1 plus 2, that is g1 of 3 into w4 1. So the graph for this is, the butterfly diagram for this is something like this. Here if we see p11 of 0, it will be equivalent to g1 of 0 plus g1 of 2, so a summation sign here. p11 of 1 will be equivalent to g1 of 1 plus g1 of 3. Similarly, p12 of 0, it's an odd sequence, so we will have a multiplication by dual factor and we will have minus sign, so it will be equivalent to g1 of 0 minus g1 of 2 multiplied by w4 0. Similarly, p12 of 1 will be equivalent to g1 of 1 minus g1 of 3, so we have g1 of 3 multiplied by minus 1 here, so it will be g1 of 1 minus g1 of 3 whole multiplied by w4 1. So this is as far as the even sequence of x of n is concerned, that is g1 of n. So we have broken down the g1 of n, that is the even sequence of x of n, into two sequences, that is even and odd, p1 of 1 of n and p12 of n. So from from n by 2, now we need to find, so we have found the n by 2 point DFTs, now we need to find n by 4 point DFTs. So in our case, n is 8, so 8 by 4 is 2. Now we need to find 2 point DFTs for this. For how many samples? These 4 samples, right? This is the even part of x of n. Now we need to go to the odd part of x of n. The odd part of x of n is g2 of n. We'll again divide that g2 of n into even and odd sequences. So suppose it is divided into p21 of n and p22 of n. p21 of n is an even sequence and p22 of n is an odd sequence. Similarly, as in case of p11 of n and p12 of n, we'll derive the values equations for p21 of n and p22 of n. It's written here. So again, these equations will be defined for n is equal to 0 to 1. Fine, because they are equal subdivisions of g2 of n. g2 of n has 4 samples, so 4 divided by 2 is 2. So each of them will be having 2 samples. Fine. So these are the 4 values by substituting n is equal to 0, 1 in p21 of n and p22 of n. So n has a range of values from 0 to 1, 2 values here, 2 values here, 2 plus 2 is 4. So we'll have 4 values, p21 of 0, p21 of 1, p22 of 0 and p22 of 1. Fine. This is the butterfly diagram. This is similar as in case of the g1 of n, right? So suppose here this is p22 of 1, this will be equivalent to g2 of 1 minus g2 of 3, g2 of 1 minus g2 of 3, so g2 of 3 is here, and this is multiplied by -1, so we get minus g2 of 3. So we'll be having a summation sign here, right? So it will be g2 of 1 minus g2 of 3 whole multiplied by w41. So whole multiplied by w41. Fine. So now again, in case of this, we need to find n by 4 point DFTs. So this is the last step, because 8 by 4 is 2 point DFTs. So beyond 2 point DFT we cannot go. So this last step will be finding 2 point DFTs. So how many 2 point DFTs we need to find? We need to find 4 2 point DFTs, because n is 8. So we have 2 plus 2 plus 2 plus 2. So that is total of 8. So now we need to find 4 n by 4 point DFTs, that is P11 of k, P12 of k, P21 of k, and P22 of k. P11 of k and P12 of k, these are associated with G1 of k. P21 of k and P22 of k, these are associated with G2 of k. Now again, the range of k here will be 0 and 1, right? So and the range of n will be also 0 and 1. So P11 of k will be equivalent to the normal formula for DFTs, n running from 0 to n minus 1. So 0 to number of samples is 2, minus 1 is 1, 0 to 1, P11 of n, Wn raised to n k. Fine. So now we have k running from 0 to 1 and n running from 0 to 1. So we have, I will write here k from 0 to 1 and n from 0 to 1. Fine. So for k is equal to 0, this will be k equivalent to 0 here. So I'll substitute 0 here. So it will be P11 of 0 is equal to summation n running from 0 to 1, P11 of n, Wn, n into k0, it's 0. So Wn 0 here. So I will get P11 of 0, n is equal to 0. I will break this summation down. P11 of 0, Wn, n is 0. So 0 into 0, 0. So then plus, now n is equal to 1. P11 of 1, Wn 0, n is 1, k is 0, that is 1 into 0 is 0, right? So we know Wn 0 is equivalent to 1. So I can write this as P11 of 0 plus P11 of 1 into Wn into 1, because Wn 0 is 1. Fine. So now coming to second value, that's when k is equivalent to 1. This will be equivalent to P11 of 1 summation n running from 0 to 1, P11 of n, Wn, n into 1, because k is 1. So this will be equivalent to P11 of 0, Wn 0, because n is 0, so 0 into 1 is 0, plus P11 of 1, I have written W2 here. Why? Because number of samples here are 2. So value of n will be equivalent to 2. So that is W2, n into n is 1. That is 1 into 1 is 1. So if we look at the two-dose vector graph, which is here, right? So we have only 2 samples. One, they will be at the opposite end of each other. So W2 0 is 1. So opposite to it will be W2 1. It will be opposite of W2 0, that will be minus 1. So instead of W2 1, I can write minus 1. So this will be equivalent to P11 of 0. Instead of W2 1, I will write minus P11 of 1. So this is, I got values of P11 of 0 and P11 of 1. Fine. Okay, this is butterfly 2-point butterfly for P11 of n. Now if we look here, P11 of 0 is equivalent to P11 of 0 small plus P11 of 1. So P11 of 0 is equivalent to P11 of 0 plus a summation sign here, P11 of 1. Similarly, P11 of 1, this is an odd part, so we will be having a minus sign here. So P11 of 1 is equivalent to P1 of 0, right, and like here, minus P11 of 1 minus P11 of 1. Fine. So this is 2-point butterfly for 2-point DFT. Fine. Similarly, butterflies for since we'll be having 4, we have to find out 4 2-point DFTs. Well, this is for one of them. Rest of the 3 will be similar. The flow will be similar. So these are the butterfly diagrams for the rest of the 3. Say for example, in this case, the P21, this P21 will be equivalent to P220 minus P221. So P220 here, and this P221 is multiplied by minus 1. So P220 minus P221. So now, so we have 4 2-point DFTs here. Before this we had 4-point DFTs, and before that we had 8-point DFT. So we need to combine them. We need to combine all the butterflies into one. So the graph will be something like butterfly. The final butterfly for the 8-point DFT will be something like this, which I have drawn here. If you notice here, then the multiplication by tuple factor is always for the odd sequence. So it's multiplication by W80 to W83 here, and then the multiplication by, it's for the odd sequence of G1K. So it's for the W40, W41, G2K, W40, W41. Similarly, here we didn't have the multiplication by W20. So even if we add here multiplication by W20, it will maintain a uniformity, but it will have no impact, because multiplication by W20 is always 1, because W20 is 1. So this is the final 8-point DFT decimation frequency, because we have decimated using frequency domain, and we have decimated using X of K FFT. Fine. So I'll stop here.